Majorana 1. In the simplest terms, what is it?
Well, at its core, it's Microsoft's first purpose-built chip, specifically designed for quantum computation.
Right.
And the key takeaway is that it's engineered to tackle these ridiculously complex problems that would just take forever on even our most powerful computers today.
Oh, wow. So a quantum computing chip, that sounds fundamentally different from, like, the chip in my phone. What makes it so unique?
You hit the nail on the head there.
Yeah.
You see, our everyday computers, the ones we're all familiar with, they rely on the principles of electronics.
Yeah.
Using bits, which are essentially like tiny switches that are either on or off, representing a 1 or a 0.
Yeah.
Quantum computing, though, taps into this whole other realm, the mind-boggling world of quantum physics. That's the science that governs those super tiny particles, the building blocks of our universe. And the amazing thing is that by harnessing these quantum phenomena, these chips can actually carry out calculations in entirely new ways, and they can do it so much faster.
So instead of regular ones and zeros, we're talking about qubits, right?
Exactly.
And this Q&A that we've got here, it mentions these things called topological qubits. What are those all about?
Excellent point.
Right.
So topological qubits are a specific type of quantum bit, or qubit as we're calling them. Now, to wrap your head around a qubit, think of it like this.
Right.
Compare it to a regular computer bit.
Yeah.
Like we said, a bit can either be a 0 or a 1.
Right.
But a qubit can be a 0, it can be a 1, or, and here's the kicker, it can be both of those states at the same time.
What?
It's true. Think of it like a coin spinning in the air until it lands. Is it heads or tails?
Well, it's kind of both, right?
Exactly. It's neither definitively one or the other. It's in this in-between state. And that's what we call superposition in the quantum world. It's not just that we don't know yet. The qubit genuinely exists in this sort of fuzzy, probabilistic blend of both states until we actually measure it.
Wow. It's like a coin flip of information that hasn't landed yet. Okay, I think I'm getting that. But why are they called topological? What makes these qubits so special?
Great question. The topological part refers to how these qubits are actually designed to be super stable and resilient to errors, which is a big deal in the quantum world. Quantum systems are notoriously delicate. I mean, even the slightest disturbance from the environment can mess things up, cause them to lose their quantum state, and lead to computational errors.
Yeah, that makes sense. Things at the atomic level must be pretty sensitive.
Exactly. So topological qubits try to get around this problem by using what physicists call exotic particles. Specifically, these things called majorana fermions. They essentially act as protectors of the information, the data, encoded in the qubit. Like, imagine building a fortress that's built to withstand the most powerful hurricanes. That's kind of the idea behind topological qubits.
Oh, I see. So they're like super robust, but majorana fermions. Now that sounds like some next level physics stuff. What exactly are those?
They're definitely fascinating. The Q&A paper we have describes them as these strange particles that act as their own antiparticles.
Okay.
So think of it like, well, imagine a twin, right? But instead of being two separate people, this twin is intrinsically linked to its other half and can basically cancel itself out.
Whoa.
It's bizarre, I know. But in the world of topological qubits, the unique properties of these majorana fermions are what, in theory, provide that extra stability. They help shield the qubits from all the noise and interference in their surroundings.
So they're like self-canceling twins that protect the information.
Yeah, that's a great way to put it.
Okay, so that brings us to another term that popped up in this Q&A, the new state of matter, inside Majorana 1. They're calling it a topological superconductor. What's the deal with that?
You're on a roll with these great questions. So to understand this, we need to take a step back. You might be asking, what even is a state of matter? We all learned about the basics in school. Solids, liquids, gases.
Right.
Well, there's also plasma. And then we have these more exotic states, like this topological state. These are like special arrangements of matter with unique properties that are super relevant to quantum computing. You can think of states of matter as how atoms or molecules are arranged in a substance and how much energy they have. Like in a solid, the molecules are all packed in tight, vibrating in place. In a liquid, they're flowing around, and in a gas, they're zipping all over the place.
Right.
So a topological state is this newer, more exotic arrangement with specific, unusual properties. Now, what about a superconductor? Basically, it's a material that, when it gets super cold, can conduct electricity with absolutely zero resistance.
Zero? Like no energy loss at all.
Exactly. It's like a superhighway for electrons, no traffic jams whatsoever.
That's wild.
So, pulling this all together, Microsoft is saying that they've managed to engineer a a superconductor that also has these strange topological properties.
Okay, so they made a superconductor that's also, what was it, topological.
Exactly.
And the idea is that this creates the perfect environment for those stable topological qubits, the ones guarded by the majorana particles, to exist and do their thing.
You got it. It's like the foundation, the base material that their whole error-tolerant quantum computing architecture is built on.
Wow. Okay, so
Right.
we've got these stable qubits thanks to these unusual particles all hanging out inside this new kind of superconductor. Now, let's go back to a question that, any student learning about this would ask. How is quantum computing actually different from the computers we use every day? Like, how does it work? Our source has a really helpful analogy here.
Yeah, it does. So normal computers, they tackle problems step by step, like when you count on your fingers. They process information in a very linear way, one bit at a time, as either a 0 or a 1.
Mm-hmm.
But quantum computers, remember, they use superposition, where a qubit can be both 0 and 1 at the same time.
Right, like that spinning coin.
And they also use this other mind-blowing phenomenon called entanglement. It's a bit like having two coins spinning in the air that are somehow linked. If one lands on heads, the other one instantly lands on tails, no matter how far apart they are.
Seriously, even if they're miles apart.
That's the idea. And that's what entanglement is, this bizarre connection where two or more qubits become linked and they share the same fate no matter how much distance is between them. If you measure the state of one entangled qubit, boom, you instantly know the state of the other one, even if they're like light years away.
That's crazy. It's like they're communicating instantly, faster than the speed of light.
Yeah, it's super weird and counterintuitive. It's this interconnectedness, this entanglement, combined with superposition that lets quantum computers explore a huge number of possibilities simultaneously. And that's why they can do certain types of calculations exponentially faster than classical computers.
That's a huge difference. So what kind of real-world problems could we actually solve with these quantum computers that we just can't solve now? What's the point of all this power?
The potential applications are massive, like game-changing massive. Think about medicine. Quantum computers could simulate how molecules behave with incredible detail. And that could lead to designing completely new drugs, even personalized therapies based on your own unique DNA and molecular makeup.
Wow.
Environmental science. They could help design materials to capture carbon from the atmosphere or create super efficient catalysts for generating clean energy.
That would be incredible.
And then you have AI and cybersecurity. Quantum computers could lead to unbreakable encryption and super advanced AI algorithms that can solve problems that are impossible for our current computers.
It's hard to even imagine what that would look like.
It is. And that's just the tip of the iceberg. It's really a whole new world of possibilities.
Our Q&A mentioned that normal computers struggle with simulating atoms. Why is that such a big deal for fields like drug discovery or material science?
It comes down to the sheer complexity of it all. Simulating atoms and molecules is a computational nightmare because of all the interactions happening between the electrons and the nucleus. It's a quantum dance with a mind-boggling number of possibilities. As you try to simulate bigger and more complex molecules, the number of potential quantum states just explodes. And classical computers, they have to plod through each of those possibilities one by one, which quickly becomes impossible even for relatively small molecules.
Yeah, okay.
But quantum computers, because they use superposition and entanglement, they can explore tons of possibilities simultaneously. And that makes it possible to do complex molecular simulations in a reasonable time frame, which could revolutionize drug design and material science.
That makes sense. It's like having a whole army of computers working on the problem at once. So this all sounds amazingly promising, but the Q&A also points out that there's some pushback, some skepticism in the scientific community about Microsoft's claims about Majorana 1. What's the main issue there? What's the debate about?
It's true. While the potential of topological qubits is hugely exciting, not every scientist is fully on board with Microsoft's claims just yet. The big question is whether they've truly managed to create and control these majorana fermions, those self-canceling twin particles we talked about that are supposed to make the qubit so stable.
Right.
Because finding undeniable experimental proof that majorana fermions exist and that we can reliably use them for quantum computing has been this huge challenge in the field.
So it all hinges on these Majorana particles. Some researchers aren't convinced they're actually there and working the way Microsoft says they are in this chip.
Exactly. The skeptics are basically saying, show me the evidence. They want more proof that these elusive particles are really there and that we can manipulate them reliably. And that's fair. Quantum computing is a very competitive field, and breakthroughs like this need to be rigorously tested and confirmed before everyone accepts them as fact. It reminds us that even when there are exciting announcements, science is a process of debate, scrutiny, and ongoing verification.
Absolutely. It's good to have that healthy skepticism. Okay, switching gears a bit here. Our Q&A also mentions that India is getting increasingly involved in quantum technology. What's happening over there?
India is definitely stepping up its game in the quantum world. They've recognized how strategically important this technology is and launched this big initiative called the National Quantum Mission just last year in 2023. The goal is to develop their own quantum computers and build secure quantum communication networks within the country. And they're not just talking about it, they're putting resources behind it. Plus, big organizations in India, like their space agency, ISRO, and their defense research agency, DRDO, they're all exploring how to use quantum technology for things like making satellite communications more secure.
Satellite security using quantum tech. That sounds super high tech, like something out of a spy movie. How does that even work?
It likely involves quantum communication. As the Q&A mentions, quantum communication uses the laws of quantum physics to send information in a way that's basically impossible to hack. If anyone tries to eavesdrop or intercept a message, the act of eavesdropping itself would mess up the fragile quantum signals.
Huh.
So it's like a built-in alarm system,
Hmm.
but it's based on the fundamental laws of physics.
So if someone tries to listen in, it automatically sets off an alarm.
Exactly. And because it's rooted in the laws of physics, it's inherently secure.
So it's unbreakable.
In theory, yeah.
Yeah. Wow, that's impressive. And what about other quantum research happening in India? Besides security, what else are they working on?
Well, they've got some top-notch research institutions
Yeah.
like the IITs, the Indian Institutes of Technology, and the Indian Institute of Science, or IIC,
Okay.
and they're all doing cutting-edge research on quantum materials.
Mm.
Like those exotic topological superconductors we talked about
Mm.
that are crucial for building the next generation of quantum computers. This fundamental research is super important for India to become a major player in the quantum world and be self-reliant in this game-changing technology.
It seems like quantum technology is becoming this global race with companies like Microsoft and countries like India investing heavily in it. Before we wrap up, let's quickly go back and review those key terms from our Q&A just to make sure we've got it all straight.
Sure, great idea. Let's recap. So first up, we have the qubit, the basic unit of quantum information. Unlike a regular bit, it can be in multiple states at once, thanks to superposition. Then we have entanglement, which is that spooky connection between two or more qubits where they're linked, even across vast distances. Next, we talked about topological qubits, a special type of qubit engineered to be more stable using exotic particles. And last but not least, those exotic particles that are supposed to provide this stability are called majorana fermions.
Perfect. This has been a really cool deep dive into this complex, but honestly super exciting field. So to sum up, Microsoft's Majorana 1 chip is a big step forward in building more robust quantum computers using those potentially more stable topological qubits. While the technology holds tremendous promise for revolutionizing all sorts of fields, from medicine and material science to AI and cybersecurity, it's important to remember that the scientific community is still evaluating these claims.
Absolutely. And at the same time, countries like India are jumping into the quantum race, recognizing how important this technology is going to be for the future.
Exactly. And, you, our listener, you've now got a solid understanding of this groundbreaking technology and some of the key issues surrounding it. You've basically just had a front row seat at a super helpful student Q&A.
That's a great way to put it.
So as we sign off, here's something to think about. Even though powerful quantum computers might still be a few years away from being widely available, imagine how they could completely change the industries and areas you're passionate about.
It's mind-blowing, right?
It is. Think about new drugs and advanced materials, a revolution in cybersecurity, AI that can solve problems we can't even fathom right now. What problems that seem unsolvable today might become perfectly solvable in this new quantum era? It's definitely something to keep your eye on. Thanks for joining us on this deep dive.